So today our group would like to present about crystal growth in semiconductor technology field effect transistor.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AZEEM bin Abbas. My metric number 1220925. And I will be presenting about crystal growth mechanism. So for the first part of crystal growth mechanism is bulk crystal growth mechanisms. The foundation of every high performance transistor begins with the quality of the crystal. As we move toward 2 nanometer and 1.4 nanometer process nodes, we face the massive challenge of defect engineering. Look at the Krosowski method on the right. This is the industry standard for silicon. You can see the seed shaft rotating as it pulls the solid crystal from a molten melt. While efficient, the quartz crucible can leach oxygen into the crystal. To fix this, we now use AI-driven cooling to manage the V-to-G ratio, balancing cooling speed against temperature to minimize point defects. For even higher purity, we use the float zone (FZ) method. This is a crucible-less technique that prevents ionized impurity scattering. By ensuring carriers undefected by unintended dopants, we maximize the fundamental speed of the semiconductor. And for the second part is the epitaxial growth and surface precision. As we transition from bulk material to the active channel of a transistor, we focus on epitaxial growth. This diagram illustrates chemical vapor deposition (CVD), which is essential for building modern FinFET and gate-all-around architectures. Notice how precursors enter the system, leading to a complex gas phase reaction and eventually surface adsorption. The goal here is atomic scale smoothness. Without it, we suffer from surface roughness scattering, where carriers collide with the gate insulator boundary and lose speed. A major 2025 breakthrough involved 2D semiconductor integration. By growing single crystalline films like Bi2O2Se directly onto silicon, we've achieved mobilities exceeding 200 square centimeter per volt second, far outperforming traditional silicon channels. So, moving on to the next part, which is advanced growth for high performance. For the absolute peak of performance, we turn to molecular beam epitaxy known as MBE. This process occurs in ultra-high vacuum environment where efficient cells evaporate elemental beam for precise layer-by-layer growth. We monitor this growth in real time using a reflection high-energy electron diffraction gun or RHEED gun. MBE is the primary tool for creating a two-dimensional electron gas or 2DEG in high-performance aluminum gallium nitride high electron mobility transistors (HEMTs). The current standard is a hybrid metal organic chemical vapor deposition and molecular beam epitaxy growth process. This method is crucial because it suppresses mechanism diffusion, ensuring that the electron velocity remains high and the 2DEG is not compensated or slowed down. And for the last part of my presentation is understanding mobility limiting factors. Finally, we must understand the factors that limit the performance. As the hierarchy shows, scattering is divided into defect, carrier-carrier scattering, and lattice scattering. At the 1.4 nanometer node, lattice-like dislocations act as traps that significantly degrade speed. But as our crystal quality nears perfection, we arrive at the fundamental physical limit, phonon scattering. These are the inevitable thermal vibrations of the atoms themselves within the lattice. Our final goal is minimizing remote donor scattering through precise spacer layers in epitaxial growth. By perfecting the growth mechanisms from the bulk level to the atomic layer, we maximize switching speed and energy efficiency for the next generation of technology.
The first step in making a transistor happen during bulk crystal growth phase
We use the Czochralski method to create the substrate or the body of the FET. The doping here is simple but massive in scale. We add impurities like boron directly into the molten silicon. The goal is to create a uniform conductive background. However, a major challenge we face is that dopants don't always freeze into the crystal evenly. To address this, a 2025 study by Ma et al. Introduced a new monitoring system that adjusts the pooling speed in real time to force the dopant to distribute evenly, ensuring the entire wafer is usable. While bulk growth gives us the foundation, the high-speed channel of the transistor is often created using thin film techniques like CVD. Here, we perform in situ doping, meaning we mix dopant gases right into the reaction chamber as the layer grows. This gives us incredible precision, but there is a catch. According to recent research by Tan et al. In 2025, if we dope this layer too heavily to lower resistance, we actually slow down the electrons because they keep crushing into the dopant's atom. So, we must use a thin film growth to find the perfect balance between conductivity and speed. Finally, to define the source and drain of the fat, we move away from crystal growth and use ion implantation. This is kinetic process where we shoot high energy ions into the wafer. The reason we use this over diffusion is directionality because the ions travel in straight line. We can use the transistor on gate as a shield. The ions hit everywhere except the channel, creating a perfectly aligned source and drain. However, this violence damaged the crystal lattice. As noted by Zhang and Etula in 2021, while we can use regrowth technique for special high power devices, for standard processors, we must follow implantation with a heating process called annealing to repair the crystal structure.
Next, we move to factor affecting bulk and thin film crystal growth in fat, crystal purity and defect density. Bulk crystal growth determine intrinsic defect concentration in the substrate, point defect, vacancy, interstitial, introduce mid-gap trap state. This trap increase the carrier scattering and reduce mobility in fat channel. High defect density lead to increased leakage current and threshold voltage instability. Advanced FETs require ultra-low defect wafer to ensure uniform device behavior. You can see in the picture side of this ni, where you can see the vacancy. And next, temperature control and thermal gradient. Non-uniform temperature during growth induce the mechanical stress. The thermal gradient generate dislocation and stacking fault. Dislocation act as leakage path under the high electric field. Thermal stress affecting the dopant, diffusing, and electrical uniformity across wafer. And based on Lee et al. 2021, poor thermal control increase device variability and reduce yield. Next, dopant incorporation and uniformity, dopant control substrate resistivity and carrier concentration. Non-uniform dopant distribution cause threshold voltage mismatch. High dopant concentration increase impurity scattering and series resistance. Low dopant region are prone to punch through and off-state leakage. Based on Tour et al., precise dopant control is critical for scale and low power fat. Connect for factor affecting thin film crystal growth fat channel. So first one is substrate and interface quality. Interface quality determine gate control over the channel. Poor interface induce high interface trap density. Interface trap degrade threshold swing and mobility. Lattice mismatch induce the strain and misfit dislocation. Multi-gate FET are highly sensitive to interface defect based on SZA and NG 2021. And for the second point is substrate temperature and atom mobility. Low substrate temperature limit atoms phase diffusion result in amorphous or polycrystalline thin film grain boundary act as change trapping and scattering center. High temperature promote especially growth and improve crystallinity. Excessive temperature may cause in the diffusion and thermal damage, based on Lee et al. Next is film thickness and strain control. Ultra thin film improve electrostatic gate control, reduce short channel effect in scale fats. Thin film increase sensitivity to interface roughness. Thicker film may relax strain through the defect formation. Thickness must be optimized for performance and reliability, based on Tour et al. 2020. And for deposition rate and film uniformity, high deposition rate lead to rapid nucleation. Produce small grain and high grain boundary density. Grain boundary reduce carrier mobility and on-state current. Low deposition rate allow large grain formation. Uniform film improve device to device consistency based on Collinger 2020. Grow smooth and surface roughness. Layer by layer grows yield smooth channel surface. Smooth surface reduce surface roughness scattering. Iceland grows cause Ross discontinuous film, Ross surface degree mobility and electrostatic control. Surface roughness effect dominate in nanoscale fat based on SZE 2021. And pros grows annealing reduce the point defect and grain boundary, improve crystallinity and carrier mobility, reduce interface strap density, enhance threshold voltage stability and reliability, essential for high performance and long lifetime fats.
My name is UMAR Khan bin Muhammad Khalid. So I will explain about the application of crystal growth in FET, or we call it field effect transistor. So when we talk about the FET, sometimes we focus on the circuit design, but actually the performance of the FET is come from how we grow the crystal to their specific application. So for standard silicon MOSFET that we found in our CPU or memory, we start with a massive crystal silicon. So then we use a Kraskowski method that are primary technique to produce this large and high purity silicon bursts, which provide a uniform substrate need for complex integrated circuit. However, then we need when we need AZEEM purities at parts per billion level, we turn to float zone growth. This specific method avoids the oxygen contamination from quartz crucible, ensuring this material is clean as possible for higher performance application. The second application is high speed and RF transistor. So since we are moved into a 5G communication and satellite tech, so we standard silicon hits its limit. So this is where specialized FET like high electron mobility transistor comes in. So to build this, we use a molecular beam epitaxy (MBE), which allow us to grow film one atomic layer at a time under an ultra high vacuum. So this precision is vital for creating heterostructures, layers of different semiconductors traps electron in a two-dimensional. So this allows for ultra fast electron movement. Additionally, for gallium nitride GaN FET, we utilize a metal organic chemical vapor deposition. This technique is widely used for GaN silicon production because it allows for high throughput manufacturing of transistors that are smaller and much more efficient compared to the traditional silicon version. We move to the second application, which is a cutting-edge organic field effect transistor. So these are the foundation of future tech like rollable display, smart screen, and wearable head mounters. So unlike a rigid silicon, this crystal can be grown directly from solution like mezzanine and other substrates. So why does crystal growth matter here? Because FET made from a single crystal organic material that have carrier mobilities order of magnitude higher than a thin film. So by growing perfectly ordered molecules, we eliminate the traps that usually slow down the electric charge, allowing flexible devices to perform at a high speed. So for next generation power FET, especially those used in electrical vehicles, require a material with a wide bandgap like silicon carbide or SiC. So with the growing of SiC, its a high intensity process, so we typically use a physical vapor transport or PVT at a temperature exceeding 2000 degrees Celsius. So the benefit of this grow crystal is clear. The enabled FET can handle much higher voltage and heat than silicon. So this is the key to reducing energy loss in EV power converters, making our transportation more efficient, and we can save the energy. To the second application, which is a cutting-edge organic field effect transistor. So these are the foundation of future tech like rollable display, smart screen, and wearable head mounters. So unlike a rigid silicon, this crystal can be grown directly from solution like mezzanine and other substrates. So why does crystal growth matter here? Because FET made from a single crystal organic material that have carry mobilities order of magnitude higher than a thin film. So by growing perfectly ordered molecules, we eliminate the traps that usually slow down the electric charge, allowing flexible devices to perform at a high speed.
Okay, that's all from us about the crystal growth in fat. Thank you.